A massive star burns through its fuel until it hits a dead end, iron. Without the outward pressure of nuclear fusion to support it, gravity wins. This collapse triggers the moment the core's mass crosses a precise mathematical boundary, 1.4 times the mass of our Sun. This is the Chandrasekhar Lahat, discovered by astrophysicist Subramanian Chandrasekhar. In a fraction of a second, gravity forces electrons to merge directly with protons, creating a flood of raw neutrons. The resulting shockwave blows the star's outer layers into space. What remains is a sphere just 20 kilometers wide, packing the entire mass of our Sun into the size of a city. At a distance, it is easy to picture the resulting neutron star as an inert cosmic paperweight, a heavy, static lump of matter frozen in the dark. But these spheres are dynamic. They can rotate hundreds of times a second and project the strongest magnetic fields in the observable universe. Gravity and magnetism this extreme would instantly tear apart normal atomic structures, rendering physical probes useless. To understand what happens inside, physicists have mapped the interior theoretically, layer by layer, down to the point where established physics ends. The descent begins at the outer crust. This is a rigid, crystalline lattice of heavy iron nuclei, locked in place by a gravitational pull 200 billion times stronger than Earth's. Moving deeper into the inner crust, the pressure forces these nuclei to absorb so many neutrons that they can no longer hold them. Neutrons begin to drip out, creating a free-flowing fluid between the structures. Further down, the crush of gravity competes with electromagnetic repulsion. Spherical nuclei warp, stretching into long rods and flattening into parallel sheets, a configuration called nuclear pasta. These compressed sheets lock together, forming one of the strongest materials in the universe. Yet, despite its extreme density, this pasta is merely a rigid shell protecting a much stranger, fluid interior. Plunging into the outer core, the pressure is so intense that the boundaries of individual atomic nuclei dissolve entirely into a continuous, liquid sea of neutrons and protons. As the newborn star radiates its heat away through neutrino emission, the falling temperature allows subatomic forces to reorganize the interior. The strong nuclear force compels these particles to stop acting as individuals. They lock into delicate quantum partnerships known as Cooper pairs. Because they are paired, they now act as a single, unified wave, gliding past one another without internal friction or resistance. Physicists classify this frictionless state as a superfluid, and because protons are involved, it is also a perfect electrical superconductor. Finding a delicate, perfectly frictionless quantum fluid inside the most violently compressed object in the cosmos defies everyday classical physics. This creates a physical paradox. If a superfluid cannot experience friction, how does it physically rotate along with a star spinning hundreds of times per second? Nature provides a fascinating loophole. The superfluid mimics rotation by forming billions of microscopic, quantized whirlpools called vortices. Over time, as the star naturally slows its spin, these quantum vortices try to move outward, but they snag on the rigid lattice of the inner crust, building up rotational tension until they violently snap loose. This sudden release of energy jerks the crust forward. Astronomers observe this as a pulsar glitch, a tiny, abrupt jump in the star's rotation rate visible to telescopes on Earth. We can detect these sudden rotational jumps from thousands of light years away. They are the observable, macroscopic proof that quantum mechanics dictates the behavior of an entire star. At the absolute center lies the inner core. Densities here reach 1 billion trillion grams per cubic centimeter, conditions impossible to replicate in any laboratory on Earth. Here, certainty ends. Matter could remain protons and neutrons, it might transform into unstable hyperons, or melt into a quark-gluon plasma. To solve this, scientists rely on cosmic collisions to measure the star's exact size and density. As these stars spiral closer, they emit expanding ripples in spacetime. By observing gravitational waves, researchers listen to how the core deforms just before they merge. Catching these fleeting gravitational ripples requires massive Earth-based physical infrastructure to measure distortions smaller than a proton. The inner core forces humanity to use cataclysmic astronomical collisions just to probe the smallest subatomic mysteries. Zooming back out, we view the complete star as a cosmic-scale particle physics experiment, testing the limits of matter in ways no Earth-bound lab can match. Scientists pair the gravitational wave data from these collisions with orbital observatories that catch the high-energy light and radiation thrown out by the mergers. Measuring the exact squishiness of these merging cores allows scientists to map the density of the superfluid interior. This link between astronomical data and subatomic behavior demonstrates that quantum rules can dictate the physics of an entire star. Inside this object, subatomic quantum rules dictate the behavior of a city-sized sphere. Neutron stars force the absolute extremes of gravity, the strong nuclear force, and quantum mechanics into a single, violent compromise. They stand as the ultimate boundary line in astrophysics, offering our only window into the absolute limits of matter itself.